Good afternoon, ladies and gentlemen. So now we'll move into the next section on traffic analysis and dispatching. So our first paper is around enhancing the inverse stops passenger method using Monte Carlo simulation, presented by Lutfi Al-Sharif, or Dean of Engineering Technology and Professor of Electrical Engineering at Al-Hussein Technical University in Jordan, and also co-authored by Matthew Appleby and Richard Peters of Peters Research.
Okay, thank you, Graham. Good afternoon, ladies and gentlemen. I just like to start usually with an irrelevant slide and end with an irrelevant slide. So irrelevant, not irreverent. So this is actually quite topical with all of the energy problems that we have. This is the Norwich in Wales. I know some of you might know the place. Some people call it Electric Mountain. And it's a storage. So this is actually an old slate mine, disused slate mine, filled up the top with water. The bottom, there's water as well. And what they do when the grid is under pressure, they will actually let the water down, get power to power the grid. Very ingenious concept, very, very clever. So I'm sure most of you are painfully aware of what Monte Carlo simulation is. You've been to the previous sessions. So the idea here is to apply Monte Carlo simulation to something called the ISP method. So I'll talk about the objectives of this piece of work, co-authored by Matthew and Richard. What the ISP method is, and then I've used a very simple term, ISP using MCS or ISP by MCS, and then we'll talk about some of the results. So the objectives, this is Richard's vision. Where's Richard? So let's see if this is a accurate interpretation. This is what Richard would like to do. He would like to go into a lift and put an accelerometer on the floor, and then let the accelerometer just keep on recording the acceleration. Get the recording, acceleration recording from the signal, and from it derive the velocity and position of the car, and then derive the number of passengers. So this is this is correct. And this is basically, it's an automated passenger survey, but without using any electrical connections to the controller, without human observers, and without the use of any cameras and artificial intelligence. So there is actually merit to the concept, the idea that you want to do a survey, count the number of passengers without actually having access to these three, which you would do if you wanted to normally do a survey. This is actually what we measure with an accelerometer. We don't actually measure speed. We don't actually measure position. What we do measure is this bit. So that's accelerating going up, and that's sort of accelerating and decelerating going up. And that's all we have. We don't have anything else. And from it, so this is taken from Richard's work. So there's an actual acceleration signal. Integrate, we get speed, and integrate, you get position. And this is interesting about position. So you can see we've moved up around 80 meters up in this case. We started at this position, we ended up at this position. So integrating twice, you get position. This is the important bit. Measure acceleration and you know your position. And the position will be positive and negative. So if you went down, it will go negative as well. So this is the idea of the accelerometer. Richard, I can't move forward. Okay. And this is what we call a seismic accelerator. This is the conventional accelerometer. What you will notice, we have a Z. It's a triaxial, an X and a Y. I've usually been more used to the Z being the vertical direction, but it doesn't matter. So this is the conventional seismic accelerometer, a mass and a spring. These are interesting. These are MEMS, micro electromechanical system accelerometers on a chip, basically. So you're talking about a size of probably this large, very, very attractive. And in fact, this is what you will have in your phones. So each one of you actually has an accelerometer in your phone, a triaxial accelerometer. And you go to Google Play, a Google Store, sorry, and just type the word accelerometer. You can download one. You can use it in a lift. And you can get the signal. You can then download it, integrate it twice. So that's all about accelerometers. So 32 years ago, This is when it started. I went to Manchester, Dr. Barney, lots of hair there, and nice jumper. Large glasses. So that was with Dr. Barney. So predictive methods in lift traffic analysis, and that was the start of the ISP method. It's a fancy name, predictive methods. It stops the passengers, that's all it is. But we like fancy names, academics. So this is the equation by Bassett-Jones, 1923. And basically what Bassett-Jones says, from the stops, from the passengers, we can actually get the stops. So what you can do very simply is invert that. And if you invert it, you say from the stops, we can find the passengers. So now the original problem was actually analytical. So we're using an equation and using the equation to, that was very, very limited. Now with the presence of Monte Carlo simulation, you can repeat this scenario 100,000 times. And you use lots of scenarios. And this is the building. This is a fictitious building, 13 passengers. So we assume that we're serving 13 passengers every round trip. Number of floors, 10, 8 above, 2 below, or 2 entrances. Entrance bias, so 30% coming from the car park, 70% coming from the ground floor. And we're repeating. Now, that sort of computer power, I don't think existed 20, 30 years ago. You needed a mainframe and whatever and so on. You have that now. So you have that now on a laptop easily. And this is the sort of table you come up with a lookup table. So once you repeat this 100,000 times, you find that it's actually impossible to have one stop in the up direction because each passenger must generate 2 stops. It's improbable. The orange ones are improbable. And then you have from the number of stops, you can find the number of passengers. So if you had 4 stops in the up direction, you infer that there were 5 passengers behind it. If you had 9, there were 12.2 and so on. And you have 1 for the down direction, 1 for the up. If you have a different type of traffic, this is where this method excels now. So we start putting different types of traffic, different mixes of traffic. So the first mix of traffic was, and this was impossible. This would have been impossible to do with an analytical equation. With Monte Carlo simulation, just enter the building, enter the mix of traffic and carry on. Lunchtime, 45, 45, 10. Afternoon peak, if we can call it that, it's 10 incoming, 85 outgoing, and 5%. And the same, you get an up table and a down table. So basically what you do, you count the number of stops in the up direction, get the passengers, you count the number of stops in the down direction and get the passengers. And then you start accumulating it. And you can here see the table in more detail. So 7 stops, 9.7 passengers. 8 stops in the down direction, 6.1 passengers, and so on. From this, then this is positive for up passengers and negative for down passengers. And you can see in Monte Carlo simulation, we know actually what happened. So we know the real number of passengers. We can compare the two. So you can see the similarity and obviously the differences there. So the conclusions. The ISP method is an old equation-based method used to infer the number of passengers from the number of stops. It's an analytical method, and as we were discussing this morning, analytical versus numerical. Analytical is very limited because you start deriving an equation and it becomes very, very difficult and complicated, but it's very limited in scope. That piece of work was only for up peak and a specific building. Now, by introducing Monte Carlo simulation, we can come up with a lookup table which is specific to that building. So I know the building, I know the traffic pattern at the time of the survey. So we run a Monte Carlo simulation, which can probably take 10 seconds, 20 seconds. It comes up with a lookup table. You save the lookup table in the accelerometer, for example, application, and then you can measure the stops and infer the passengers. Where this is weak, these tables have assumed a fixed number of passengers, P in each round trip. Now, that's not necessarily true. So the method needs to be enhanced to be able to detect the number of passengers in each round trip and then adjust the table accordingly. So this is the next piece of work, enhancing that so that it actually can cope with any number of passengers. I'll leave you with a closing slide. This is Leipzig. It's an interesting monument to the Battle of the Nations. 1813, that battle happened, and the monument was finished 1913, 100 years later. It's quite impressive, actually, when I visited that, these figures at the side. So I just thought I'll leave you with that interesting. At least if you don't remember anything, you remember the first slide. What was that? The Norway, and the last slide, and forget the rest. Thank you.